The first situation we're going to look at is actually the most straightforward, which is to find the electric field outside a sphere. Now notice that this isn't a point charge, and we're not even trying to simplify it down to a point charge. So if you think you know what the electric field is outside a sphere from one of the earlier sections in the book, note that it has been told to you, but it was not derived in any way. So this is actually the best way to derive it, otherwise the math is way too hard. So first we notice that if we just focus here on our charge distribution, it's a sphere, so it has spherical symmetry. We can then assume that the electric field also has spherical symmetry. That means that we should choose a Gaussian surface that has spherical symmetry, i.e. a sphere. And note that it should be centered. So the center of our charge distribution is also the center of our Gaussian sphere. And notice that capital R here is going to be the radius of the sphere itself, and then lowercase r is the radius of our Gaussian sphere. Don't make the mistake of thinking, hey, since the charge distribution was a sphere, I have to choose that sphere to be my Gaussian surface. That's not right. You want this to be an arbitrary r that is larger than the radius of your charge. So since we know that everything is radial, there's going to be this nice simplification where everywhere on the sphere our electric field should have the same strength because the symmetry demands it, and we see that it is always parallel to our a vector, which means it's perpendicular to the surface. So remember that perpendicular to the surface means we're going to be able to do multiplication, so that simplifies our surface integral nicely. And our goal is really to find the field strength outside the sphere. So start from this. This is your starting equation. Now, one thing that you're going to need to get used to is even though I'm writing down on the left flux, I don't actually care what the flux is, in a way. I basically care about these two parts. And Gauss's law was this equal sign, really. So this is the definition of flux here. And then Gauss's law was actually saying that, oh, these two things are the same. So that's a little tricky here. So what we're really doing is using Gauss's law to set these two things equal to each other. But really, having all three of them equal is the best starting point. So we're going to do that, and we're going to look at our symmetry and our picture. Again, visualizing is really important to say something about what's happening. And in particular, we see that because E and dA are parallel, i.e. our electric field is perpendicular to the surface, we get to multiply these. Now the next thing we see is that the entire charge of the sphere, which was capital Q, is enclosed. So the charge enclosed is just Q, and this whole thing just simplified nicely because of the symmetry. So now what we need to do, again, the goal is to say, hey, what's E, is to define what A is. And A is just the surface area of a sphere. We know what that is, 4 pi r squared. Be careful, this is not capital R, remembering that capital R is the radius of the sphere of charge. This is now lowercase r. Lowercase r is the radius of our Gaussian sphere, which is where we're doing the integral, so that's what we want the area of. So 4 pi little r squared. That's multiplied by E, which is again the thing we're trying to figure out. And so now we rearrange and boom, there you go. Now, you might look at this and say, hey, this looks just like the electric field from a point charge, and that's true. It isn't equal, because in particular, this is only for the case that R is greater than capital R. So it's not exactly the same. In the next video, we'll talk about what happens when they are flipped so that you are actually inside the sphere. And so the best way to define this is to say that your electric field vector is equal to 1 over 4 pi epsilon naught Q of that sphere over r squared. It can be helpful to use capital Q to remind yourself that this isn't a point charge, but that's really just notation. And then you need your direction. What's the direction? R hat. It points radially away from the center, but then you specify that this is when the radius you're looking at is greater than the radius of the sphere. So that's actually our answer. Now keep in mind that we got this actually from symmetry. I knew what symmetry my charge distribution had, so I knew what symmetry my electric field had to have. Nowhere in the math did you get this, and if you have it wrong, the math won't work out, it won't make any sense. So this is the simplest application of Gauss's law, but it actually would be next to impossible if we did it using the Coulomb method we learned in the previous chapter.